recall the first derivative test. It states that if the derivative of f changes its sign from negative to positive as x increases through a point A, then A is the point of local minima. And the local minimum value of the function is the value of function f at A. Also, if the derivative of f changes its sign from positive to negative as x increases through a point A, then A is the point of local maxima, and the local maximum value of the function is the value of function f at A. In addition to the first derivative test, there is another test known as the second derivative test, which is quite often used to determine the local maxima and local minima of a function. Let's learn about this test in detail. Consider a function f defined on an interval I. Let A be any arbitrary element in the interval I. Let us suppose that the given function f is differentiable at A twice. If the first derivative is equal to 0 and the second derivative is negative, then A is the point of local maxima, and the local maximum value of the function is f of A. Also, if the first derivative is equal to 0 and the second derivative is positive, then A is the point of local minima, and f of A is the local minimum value of the function f. The second derivative test fails if both the first and the second derivatives are equal to 0. Let's prove the first part. Given that the derivative of f at point A is 0 and the double derivative is negative at point A, using the first principle of derivatives, the second derivative of f at point A can be defined as shown. We have that the first derivative of f at point A is equal to 0. For a sufficiently small h, the first derivative of f, a plus h, upon h will be less than 0. Now two cases arise. The value of h may be either negative or positive. Suppose the value of h is negative. Then the first derivative of f at the point a plus h should be positive. Suppose the value of h is positive. Then the first derivative of f at the point a plus h should be negative. Observe that as the value of h is increasing from negative to positive, the value of the corresponding first derivative is decreasing from positive to negative. Hence, from the first derivative test, the function has a local maximum at point A. The value of the function at point A is local maximum value. Similarly, we can prove the second part. The second derivative test fails if the second derivative is also 0. In this case, we follow the first derivative test. Now, let us learn the working rules to find the local maximum and local minimum values. Begin by finding the derivative of the first function and equate it to 0. Suppose the values of x are x1, x2, x3, and so on. Then, find the second derivative of the given function. After that, find the values of the second derivative at points x1, x2, x3, and so on. If the values of the second derivative at these points are negative, then the function has local maximum values at these points. If the values of the second derivative at these points are positive, then the function has local minimum values at these points. Local maximum or local minimum value is the value of the function at these points. Let's learn this with the help of an example. Let f of x be a function given by 2x cubed minus 21x squared plus 36x minus 20. We have to find the local maximum or local minimum values of this function. On differentiating with respect to x, we get the derivative as 6 into x squared minus 42 into x plus 36. For function f to have local maxima or local minima, its derivative should be equal to 0. On simplifying, we get the equation as x squared minus 7 into x plus 6 is equal to 0. Solving the equation, we get the values of x as 1 and 6. Now, we will find the second derivative. The second derivative of f is equal to 12x minus 42. The value of the second derivative of the function at x is equal to 1 is minus 30. This shows that the second derivative of f at 1 is negative. Hence, the function has local maximum value at x is equal to 1. Hence, the local maximum value of the function is minus 3. The value of the second derivative of the function at the value of x is equal to 6 is 30, which is a positive value. Hence, the function has local minimum value at x is equal to 6. The local minimum value is minus 128.